So, in the previous lecture, we discussed conjecture known as the Eisenmann's conjecture. And what did the conjecture say? The conjecture said that if a LTI system with a constant gain k is asymptotically stable for k in the range of k1 and k2, then the same LTI system, if it is in interconnection with a memoryless nonlinearity, okay, if it is in the range, if it is in feedback interconnection with a memoryless nonlinearity, that lies in the k1 k2 sector. Okay, so the memoryless nonlinearity is in the k1 k2 sector. So we'll denote this sector as we progress as this. Then this is also asymptotically stable. Okay, so this is what the Eisenmann's conjecture was. Well, the Eisenmann's conjecture is wrong. Okay, this conjecture does not hold in general for all LTI systems. Okay, so if it satisfies, if the so the LTI system, if it satisfies certain properties, then only whatever idea this conjecture has given, it will actually hold. Okay, so what I'm saying is, though the Eisenmann's conjecture as it is not correct, but not correct because it is talking about all the LTI systems. This the property that has been stated here, or the statement that has been made here, will hold if certain additional properties are associated with the LTI system under consideration. Okay, so this brings us to something known as passive systems. So, what exactly are passive systems? Okay, passive systems are systems that do not generate energy. Okay, whatever energy is applied to them, their response is based only on that, but they do not have any, they do not generate any form of energy. Okay, the simplest example that you can actually think of is a resistor. Okay, a resistor R. If a voltage V is applied across this circuit or this resistor, then a current I will start flowing across this resistor. Okay, so what is happening here? The resistor does not have energy on its own, so the energy that is being supplied to the circuit is minus infinity to infinity. The total energy that is being supplied to the circuit is this. And the resistor, does it store energy? No, so it dissipates whatever is being supplied. So the energy dissipated is also this. Okay, so whatever energy is supplied in this case, it gets dissipated. No energy is stored. Okay, and the energy dissipated is always positive. So what you see here is, over any time interval 0 to t, for this particular circuit, vi dt this integration is going to be greater than equal to 0. Okay, so if V is 0, I will also be 0, so there won't be any energy. But if there is some V, then there would be some current flowing, and hence it indicates that there is some energy flow or energy that is being supplied to the system. Okay, so such systems are known as passive systems. Okay, the amount of energy supplied to the system is positive. So the energy supplied is energy dissipated, and the energy supplied is over the entire time interval is minus to infinity, and over a certain time interval 0 to t is integration 0 to t vi dt, uh, vi dt. Okay, and this energy supplied, okay, to the system is essentially positive. So in passive systems, the energy supplied to the system is positive. Okay, energy supplied over any interval of time is positive. Now consider a similar electrical circuit. However, this time we'll have a energy storage element, let us say a capacitor, in series with the resistor. Okay, and to add to it, let's say that the capacitor initially has some charge Vc. Okay, and the voltage that would be applied across the terminals is V, which will result in a current flow, that is I. Okay, so at t equal to 0, the charge stored in the capacitor is some Vc, and so it's a non-zero value, is some charge stored in the capacitor. Okay, as a first case, suppose the terminal is terminals are short circuited. So in this case, what is the applied voltage? The applied voltage becomes 0. So the energy supplied, the energy that is supplied to the circuit is again integration 0 to t vi dt. Since V is 0, the energy supplied is 0. So we can still call it passive. Okay, but please note that we are analyzing it for a very specific case when the circuit is short circuited. Okay, when the terminals of the circuit are short circuited. Suppose a non-zero voltage V is applied across the terminal. Suppose this is what is done. Across the terminals, you have supplied a non-zero voltage V such that the voltage that is being applied is less than Vc. So the voltage that is being applied is less than the potential that is there across the capacitor that you have in hand. Okay, suppose this is the case. Now what will happen? In this case, the capacitor will actually discharge, and the current flow will be from the circuit to the source that has been connected. Okay, so what is the energy supplied in this particular case? So the energy supplied in this particular case, again in the interval 0 to t vi, where I is the current, vi dt, and this thing is no more positive because the current here is flowing in the negative direction. So vi dt integration 0 to t is going to be negative, and hence this is going to be less than 0. Now since this is negative, earlier we had said that for the system where the input and the output product is the integration of the input and the output product is going to be greater than equal to 0, then we'll call it passive system. Or rather, if the energy supplied to the system is positive over a time interval, then we'll call it a passive system, right? Now Here we saw that when we short circuited, the energy supplied to the system is zero, so it still qualifies for a passive system when you have a RC circuit. But when we apply a voltage V across the terminals of the RC circuit, such that the voltage applied is less than the voltage potential across the capacitor terminals, then in this case the energy supplied to the circuit becomes negative. So it looks like it is not a passive circuit. But then the question arises is, where did the charge, or where did the okay from where did the energy in the capacitor come from? The capacitor didn't generate any energy on its own. Okay, so someone would have supplied this energy into the capacitor. So instead of looking for the energy supplied over a particular time interval, for this circuit, if you look into the energy supplied over the entire time interval, minus infinity to plus infinity, from the past till the end of time, if you see, then this is going to be greater than equal to 0, and this is going to be passive. So this says that the system is passive. So for passive systems, the energy, total supply of energy, needs to be positive. Okay, now uh, this brings us to something which is interesting as far as this circuits with energy storage elements are considered. Okay, so the energy that is being supplied, the total energy that is being supplied to a system is equal to the energy that is dissipated plus, so this is the total energy dissipated plus the total energy stored in the circuit. Okay, so in case of an electrical circuit, the energy dissipation would be in terms of heat as the resistor gets heated up, and the total energy stored in the circuit in case of electrical circuit is either in the form of electrical energy, which is when capacitors are involved, or in the form of magnetic energy, which is when inductors are involved. Okay, so this essentially, for an electrical circuit, would look like the total energy supplied is equal to total energy dissipated plus the total energy stored. Okay, so total energy supplied is energy dissipated plus the energy stored. So this equation that you have here, I've written it for an electrical circuit, I'll state it in general how it would look like, is known as the dissipation equality. Okay, so if the input is U and the output is Y, and the total energy supplied is this is equal to, I should say, total energy dissipated plus total energy stored. Okay, so this is the dissipation equality. Okay, so this can also be stated as what? This is nothing but this is equal to, or rather I should put it like this. So from this dissipation equality, what you see is the total energy supplied minus the energy stored is nothing but total energy dissipated, and the energy dissipated is always greater than equal to 0. So for a passive system with energy storage elements, okay, for a passive system with energy storage elements, this inequality holds, and this inequality here is known as the dissipation inequality. Okay, this can also be written as u transpose y minus d by dt of energy stored should be greater than equal to 0. So this is indicating what? That the that the power that is being, or energy supplied per unit time, minus the rate of change of energy stored. Okay, so energy supplied per unit time minus the rate of energy stored should be non-negative for a passive system. So this has to be true for a, this holds for a passive system. Okay, so this is the main inequality. If there is no energy storage element, then u transpose y will be greater than equal to 0. Okay, so this is indicating what? This is indicating that over the entire period of time, the or rather in terms of power, the supply power will always be greater than or equal to the rate of change of stored energy. Okay, so this is what the inequality is essentially stating, that the, for a passive system, so for a passive system, the supply power will be always greater than or equal to the rate of change of stored energy in the system. Okay, so this is what will always hold for a passive system. So essentially, if for a system you see that the supply power is always greater than equal to the rate at which the stored energy is changing, then that system is termed as a passive system. Okay, if there is no energy storage element, then the supply power has to be positive. Now, observe one thing from this discussion that we had. So look back to the inequality that we have here. The energy stored that is being denoted here, this E for most system qualifies as a Lyapunov function. Okay, this E for most systems qualifies as a Lyapunov candidate function because the energy stored in the system is positive. Okay, now when the input u is identically 0, what do we have for passive systems? When the input u is identically 0 for passive systems, you have minus dE by dt to be greater than equal to 0, right? Which indicates that dE by dt is less than equal to 0. And this is a very important thing. Why? Because For a passive system, E qualifies as a Lyapunov candidate function, and in the absence of the input, if the system evolves on its own, it evolves autonomously in the absence of the input, then what you see is d by dt is negative semi-definite. So for E being a Lyapunov candidate function, d by dt being negative semi-definite for the system, it indicates that it indicates what? It indicates that the system under consideration is stable. Okay. So with this, passive systems are stable. Okay. In all our analysis, so you notice we are taking U transpose Y to denote everywhere. So as I had mentioned at the beginning, for all our analysis, number of inputs will be taken as number of outputs. So the analysis that we do here for this part, for the forthcoming parts, will be assuming that the number of inputs and the number of outputs are going to be the same. Okay. So this equation is also known as the, we'll name this equation as the dissipation inequality. Okay, and this is the inequality that is satisfied for all passive systems that you can think of. So we'll stop here and continue our discussion on passive systems in the forthcoming lectures. Thank you.